Let's solve an equation that has multiple angles involved. Tangent of 3x equals 1, where we have all multiples of the angles are multiples of 3. So how do we solve it? Well, where is the tangent equaling 1? That's one question we want to ask. And we also want to be careful, what's the period of tangent? The period of tangent was from 0 to pi. So I just might make a little note of myself right now so I don't forget. And so where is the tangent of 1 on that period? The tangent of 1 occurs at the point pi fourths, or the value of pi fourths. So tangent of 1 is pi fourths, which allows me to write then that 3x equals pi fourths. Because again, the tangent at 1, or the tangent of 1 is pi fourths. How do we solve this? Well, remember again that these equations don't have just one solution. They have multiple equations as long as we get the period right. So pi fourths is a solution. We know tangent is positive 1 within this period, but I'll find this next solution on a repetitive pattern every pi units past it. So I would say pi fourths plus n pi. From there, we'll want to solve for x to get x by itself, since that's what our primary goal is. So divide everything through by 3. So x equals pi divided by 12 and plus n pi over 3. So there's my solution of x. I would like to find all the values of x between 0 and 2 pi. So let's begin by plugging in our values of various integer values of n. We already know that 0 makes our value, if this was 0, our first value is at pi halves, or pi twelfths. I don't know where I went, so that's at n equals 0. If n equals 1, then I have a solution of x equals pi halves plus 1 pi, so pi thirds. Solving that to get common denominators, that's pi twelfths plus 4 twelfths pi. And that equals 5 pi twelfths. So that's at n equals 0. That's at n equals 1. This value is between 0 and 2 pi, so I can keep looking. Let's shoot for x equals pi twelfths plus 2 pi over 3. That's our next integer value. Common denominators, 2 pi twelfths becomes 12. 4, that becomes an 8 pi. So this is the same thing as pi twelfths plus 12 on the bottom times a 4 times a 4, 8 pi. And that produces, looks like that produces a 9 pi twelfths at n equals 2. I'm still within the period from 0 to 2 pi, so x equals, I'm just going to keep track. I'm going to make x equal, that's a sub 2, that's a sub 3, that's a sub 1, and that's a sub 0. So my next value, pi twelfths plus a 3 pi over a 3. That's the same thing with equivalent expressions or common denominators, would make that 12 pi, and that produces a 13 pi over a 12 at n equals 3. All right, looks like I still got some more values I can find. My fourth x I'm going to look at is pi twelfths plus 4 times pi over 3. Same thing as pi twelfths plus 16 pi over 12. That equals 17 pi twelfths. Try 5. My next solution, that equals pi twelfths plus 5 pi over 3. To get common denominators on that one, that becomes 20 pi, so that looks like that equals 21 pi twelfths. And then let's look at the next one. Since this value is still within the period from 0 to 2 pi, the sixth one, pi twelfths plus 6 pi over 3. And common denominators on that one makes that a 24. That looks like that equals 25/12 pi. That solution is beyond my restrictions here from 0 to 2 pi. So all my solutions of tangent 3x equals 1 is pi 12s, 5 pi 12s, 9 pi 12s, 13 pi 12s, 17 pi 12s, and 21 pi 12s. And I also noticed that as I was just rushing through to get you all the examples, you guys may have caught it. I can go ahead and reduce 21 pi 12ths as well. There's a common. So that would also be divide both sides by a 3. So that's what, 7/4? 12ths. So that's probably the better solution than that one. So that one's reduced. And I think I was able to simplify all the other ones as well. Well, 9 pi 12ths right there, that could be simplified as well, couldn't it? That could be simplified to 3/4 pi. All right. Have another equation that we want to solve that includes a multiple angle. So sine of 1/2 x equals √3 over 2. We want to find all the values of x that's true from 0 to 2 pi. So again, what's our process? Well, we understand that sine occurs on a period of from 0 to 2 pi. And so it repeats every 2 pi. That's good to know. Where's all the values where sine equals √3 over 2? Well, one value where that occurs at is pi thirds. The sine of √3 over 2 occurs at the value of pi thirds. And sine also has its value in the second quadrant where it's also positive, and that occurs then to find the full pi minus the pi thirds, and that equals 2 pi thirds. So I have two positions where my sine value equals √3 over 2. One's at pi thirds, and the other one's at 2 pi thirds. From there, we know that I have another solution every multiple of 2 pi past that. So plus a 2 pi, or 2n pi, plus a 2n pi are all my multiple solutions. Solve these for x. So that's x over 2 equals that. And then x over 2 equals that one. Solve for x. The top one, multiply everything by 2 to get x by itself. So I'll have x equals 2 pi thirds plus 2n pi. And the second version, I'll have x equals 4 pi thirds plus 2n pi. Next step is what are all the values that I can create with different multiples of n such that I have a value between 0 and 2 pi at n equals 0. This top one becomes 2 pi over thirds. I know that's within the interval. The second one at n equals 0, that's 4 pi thirds. All right, at n equals 1, if n were equaling 1, this would be 2 pi thirds plus 2 pi. That extends it beyond my interval. And likewise, if I had n equal 1 in the second one, that's 4 pi thirds plus 2 pi. That 2 pi again extends it beyond the interval from 0 to 2 pi. So the only solutions that make this equation true within this particular interval is 2 pi thirds plus 4 pi thirds.